show that the relation R in set A of points in the plane. So what is the given set A? The set is set of points in a plane. That is, we can write it like this, that is a set of points P, Q, R, O, whatever, but where all of them lie in a plane. And what is the relationship given? The relationship given is that the 2 points P and Q are related, PQ, such that OP equal to OQ. And what is O? Obviously, O is origin. O is origin. 0, 0. What are the coordinates of O? 0, 0. Now it is more or less a relation of equal to kind. We have been doing many times. So let me first of all check if the given relation is reflexive or not. If there is, let us before that have a diagrammatic kind of situation here. Let O is the origin and P is a point here and Q is a point here, such that OP equal to OQ. So to check the reflexive property, I say every point P is related to itself, where P lies in the set A. Why? Because OP obviously equal to OP, equal type. Every number is equal to itself. So yes, the given relation R is reflexive. Now let me check symmetric. That is, if the point P is related to point Q, means distance OP equal to distance OQ. And after all, OP and OQ are what distances? The real numbers. So if two real numbers OP and OQ are equal, then symmetric property is there in equality. So OQ is also equal to OP. So clearly Q is related to P. So P related to Q implies Q related to P here. So we can conclude that the given relation is symmetric. Now to check the transitive property, let P is related to Q. That means OP equal to OQ. And Q is related to a point S. That means OQ equal to OS. From these two, it is understood OP equal to OQ and OQ equal to OS. So OP is clearly equal to OS, and you can conclude that way P is related to S. That is P related to Q, Q related to S, and P related to S. So we can conclude that the given relation R is transitive. So what do you find? That the relation is reflexive, symmetric, and transitive on set of points in plane. So we can conclude that yes, the given relation R is an equivalent relation. We have further to find out that what type of, if we join all such set of points, then what type of its graph will be. So here let P is any point other than 0, 0. And Q is any other point which are related. So if P is related to Q, that means OP equal to OQ. Now you recollect in your junior classes, in class 9th, 10th, etc., you have done the locus of a point which remains equidistant from a fixed point. And here the condition of locus is satisfied that OP remains equal to OQ if they are related. And if they are related, then OP equal to OQ. So clearly the locus of P or the set of such points P etc. lie on a circle with radius equal to OP. Show that relation R defined in set A of triangles as R equal to T1 related to T2, where T1 is similar to T2, is an equivalence relation. That is first part. And then again we have to prove that the three triangles T1, T2, T3 whose sides are 3, 4, 5, 5, 12, 13 and 6, 8, 10. We have to find out which triangles among T1, T2 and T3 are related, that which two are mutually similar. That's what we have to do. So let's take the first part. Here, what is A? A is the set of triangles. A so given is a set A is set of triangles in a plane, and R, the relation is defined as T1, T2 such that T1 is similar to T2 and of course T1 and T2 belong to A. So first of all we have to prove it is reflexive. It is a simple question. Of course, every triangle is related to itself. T belong to, for all T, triangle belong to this set of triangles. Why? Because every triangle is similar to itself. Given is a triangle, so at least the triangle is similar to itself. So, yes, the relation is reflexive. Now, number 2, let T1 is related to T2. Means T1 is similar to T2. Do you know this is a symbol for similar triangle? If T1 is similar to T2, obviously T2 is similar to T1 or T2 is related to T1. So we can conclude that the relation is symmetric. Now number 3, let us check the relation is transitive. T1 is related to T2 implies T1 is similar to T2. T2 is related to T3 implies T2 is similar to T3. So now T1 is similar to T2 and T1 similar to T2 and T2 similar to T3 will definitely imply T1 is similar to T3 or T1 is related to T3 whenever T1 related to T2 and T2 related to T3. So clearly we can conclude that the given relation R is an equivalence relation. So that is the first part. And now let us come to the second part, that you are given 3 right angle triangle. One is with the side 3, 4, 5. Obviously are the sides of right triangle. You can check up with Pythagoras theorem. 3 square plus 4 square is equal to 5 square. And the second triangle, the sides of the second triangle T2 are 5, 12 and 13. Obviously it is a right triangle because 5 square plus 12 square equal to 13 square. This is T1, this is T2 and the third triangle T3. The length of the sides are given to be 6, 8 and 10. And clearly this is also right angle triangle satisfies the Pythagoras theorem as 6 square plus 8 square equal to 10 square. We have to see which two of them are similar. No doubt that one angle is right angle in all the 3. Then you have a SAS theorem of similarity. What is SAS theorem of similarity? Two triangles are similar if two sides, SAS means two sides are proportional and the included angles are equal. So let me take the case of T1 and T2. In case of T1 and T2, both have. Now let us consider T1 and T2 to check whether they are similar or not. Of course, the right angle, both are right triangle. Now let us take the ratio of the corresponding sides. So it is 3 by 12. The ratios are 3 by 12. Okay, let me take the smaller side to smaller side. So this 3 and 5. So ratio of smaller to smaller is 3 by 5 and the other one is 4 by 12. Obviously, 3 by 5 is not equal to 4 by 12. So, the angles are equal, but the sides containing the angle are not proportional. So, T1 is not similar to T2. Now, let me try T1 and T3. So, T1 and T3, obviously here right angles are there, and the ratio of the containing side is 4 by 8, this 4 by 8, and the other one is 3 by 6. 4 by 8 equal to 3 by 6 equal to half. Yes. So T1 is similar to T3. That is right. Let us also check T1 and T2 and T3. Of course, they are right angle, but the ratio 5 by 6 is not equal to ratio, 5 by 6 is not equal to 12 by 8. So T2 and T3 are not similar. So only one pair is similar, that is T1 and T3. Now given is a relation R on set A. What is set A? A is the set of all the polygons. All polygons. All the polygon means it may be a triangle, maybe a quadrilateral, pentagon, hexagon, any number of sides. So all such figures are there. And what is the relationship? Relationship is that two polygons P1 and P2 are related. P1 related to P2. The relation is that two polygons P1 and P2, P1 related to P2, provided P1 and P2 have the same number of sides. P1 and P2 have the same number of sides. Okay. So we have first of all to prove that it is an equivalence relation. Now let me check number one, reflexive. So every polygon P is related to itself, P related to P. Why? Because the number of sides in P and to itself will remain the same, where P belong to A, the set of polygons. So safely we can say P is every polygon is related to itself, or the given relation is reflexive on the given set on E. Number two, let me check symmetric, whether the given relation is symmetric or not. Let P1 is related to P2. What does it mean? That the number of sides in P1, let me take this symbol and P1 means number of sides in P1 is same as number of sides in P2. Obviously, number of P1 is same as P2, so number of sides in P2 should be same as number of sides in P1, or P2 is related to P1. So P1 related to P2 implies P2 related to P1. We can conclude that R is symmetric. Now number three, let us check R is transitive or not. Now let P1 is related to P2. That means the number of sides in P1 is same as number of sides in P2. And P2 is related to P3. That means number of sides in P2 equal to number of sides in P3. Obviously, if we combine the two, if the number of sides of P1 equal to P2 and that of P2 equal to P3, so it clearly indicates that number of sides of P1 is same as number of sides of P3. Or in other words, P1 is related to P3, so we can conclude that the given relation R is transitive on a set of polygons. So because R satisfies all the three properties of reflexive, transitive and symmetric, so R, we can conclude R is an equivalence relation. Now what is the second part of it? He further is asking you that given is what is the set of all polygons which are related to right triangle. We are given a right triangle of sides 3, 4, 5. Then what are all the polygons which are related to it? Now please remember, the relationship depends only on the number of sides. So whether it is a right triangle with 3, 4, 5 or it may be any triangle, what is a kind of polygon? It is a polygon of how many sides? 3 sides. So what are all the polygons having 3 sides? We call them triangle. So what is the required set? The required set, which has the same number of sides as the right triangle of side 3, 4, 5 is nothing but the set of all triangles. It is simply set of all the triangles. Let L be the set of all lines in XY plane and R is the relation in L defined as L1 and L2 are related provided L1 parallel to L2. So we have to show that R is an equivalence relation, and further we have to find the set of all lines related to line y equal to 2x plus 4 means which are parallel to this line. So that comes later. Now let us first of all, let me denote A as the set of lines in XY plane, and R is the relation such that L1 is parallel to L2. L1 is parallel to L2. Now number 1, let's check whether the relation is reflexive or not. Every line L in the given set A of set of lines is related to itself. Why? Because every line is parallel to itself, or you may take in particular that they are coincident lines. So after all, coincident lines are in particular, they are parallel. Okay. So for all lines in the given set A, so you can conclude that the given relation is reflexive on the set of all lines, that is set A. Now let us check the symmetric property. Let L1 is related to L2. L1 is related to L2. That means L1 is parallel to L2. If L1 and L2 are two lines, L1 parallel to L2, obviously L2 is parallel to L1. So that means L2 is related to L1. Okay. So clearly the given relation is symmetric. Now number 3, let's check if the relation is transitive or not. Let L1 is related to L2, means L1 is parallel to L2, and L2 is related to L3, then L2 is parallel to L3. Geometrically, this is L1, L2, L3. So if L1 is parallel to L2 and L2 is parallel to L3, then clearly L1 is parallel to L3, or L1 is related to L3. So we conclude that the given relation R on the set of all lines in a plane on A is an equivalence relation. Now the second part, what is the second part of it? The second part is that find all the lines which are related to the line y equal to 2x plus 4. Now this line 2x plus 4, if I call it L1, if there is any other line parallel to it, now using a bit of coordinate geometry, can you tell me if the equation of line L1 is 2x plus 4 and if there is any other line parallel to it, what is the relationship? That their slope should be equal. If M1 is the slope of this line and M2 is the slope of any line, then the L1 parallel to L2, then M1 should be equal to M2. What is the slope of this line, given line y equal to 2x plus 4? Obviously it is 2. So now, what is the set of all lines with slope 2? It is 2x. And what about the y-intercept? That may be any real number. So any real number. So remember, y equal to 2x plus c is the required set of all the lines parallel to the given line y equal to 2x plus 4.